Hello, everybody. Welcome back. Today we are going to finish up Unit 2. We're going to be talking about Unit 2.7, which is on VSEPR and hybridization. So let's get started. So for my students that are watching this video, I have given you access to a chart that looks like this. And there's lots of good information on here, so I would recommend not only having your periodic table out, but having this chart nearby as well. All right, so at this point, we have already gone through a lesson about drawing Lewis structures. We are also going to be talking about today the VSEPR model, which is essentially just a fancy way of saying, what is the shape of a molecule? What geometric shape does it take? We're also going to talk about hybridization today, which may be a topic that is new to a lot of you. So VSEPR, first of all, VSEPR, which probably should be pronounced VSEPR, but we just say VSEPR because it sounds better, stands for valence shell electron pair repulsion. The VSEPR model is a way of predicting three-dimensional geometric shape of a molecule, and it's based around the understanding that electron pairs, whether they're shared pairs or lone pairs, doesn't matter, repel each other. Like charges repel. So electron pairs are going to spread out in 3 dimensions as far apart from each other as possible, and that will determine the shape of a molecule. So how do you predict the VSEPR shape? First and foremost, guys, don't even try to predict a shape without a Lewis structure in front of you. Sometimes we get a little bit lazy and we start to just look at a molecule and we say, oh yeah, that's tetrahedral. Always draw it out, ladies and gentlemen. All right. And we're going to look at the chart. This chart that I gave you access to is going to help us determine, based on the positions of the atoms, what that three-dimensional shape is going to be. Okay. We're also going to look at bond angles and polarity as well. Couple of things to keep in mind before we get started. We in a Lewis structure, we always have shared pairs. We also have lone pairs. We'll come back and revisit this statement again, but just keep in the back of your mind that lone pairs take up more three-dimensional space than shared pairs do. One other thing to keep in the back of your mind, when you have a drawing that has a multiple bond, a double, a triple bond, shape-wise, that is going to count as just one shared pair. And I'll show you what I mean in just a moment. Okay, now, for those of you that are using this chart that I have given you access to, okay, there is a column over here on the far left that says electron groups on central atom. The College Board would probably, instead of that as a title of this column, they would put a heading that would say electron domains. You can use that term if you wish. You can also use a term steric number. Okay, either one of those terms is acceptable. Okay, and steric number, electron domains mean how many pairs of electrons are around the central atom. Okay, it's kind of like if you drew a box around the central atom, how many sides of the box have something on it? Okay, now this slide, all right, and subsequent slides list all of the different shapes that you need to know. Now, rather than just talking through a chart with numbers, which I think is really boring, what we're going to do instead is look at a simulation. Okay, this is from a website called PHET, P-H-E-T, and they have these wonderful simulations, and this is not the only one. There's lots and lots of them. But I like this because it's going to allow me to show you in 3 dimensions what these shapes are. Okay, so if you want to follow along with me, I'm going through that chart that I just zipped through on the previous slides. I'm also going through in order the shapes on that chart that you have in front of you. All right. I'm also going to use some of the same molecules that you drew in our last lesson. So in our last lesson, there was a slide where I asked you to draw a whole bunch of different Lewis structures for different molecules, and I'm going to pull some of those. So if you have your notes handy, you can look at some of those structures that you've already drawn. The first of which is carbon dioxide. If you look at your drawing for carbon dioxide, you will see that the carbon is in the center and there's a double bond on one side and a double bond on the other. There are no lone pairs. That means that the carbon has a steric number, or let's use the term electron domains. It has 2 electron domains. 2 sides are occupied, and there are no lone pairs. So, ladies and gentlemen, this is the shape called linear. Okay, nice and simple. Right? That is what carbon dioxide, the gas that we're all exhaling, that's what carbon dioxide looks like. Okay, you do need to know the bond angles. Okay, so which is why I'm displaying them here. All right, next, and I'm going to go kind of fast, so keep up. The next molecule, and again, this is one that we drew, was boron trifluoride, BF3. Remember, boron was one of our exceptions to the octet rule. Boron had 3 single bonds, no lone pairs. And when that happens, so that's 3 electron domains, all 3 electron domains are a shared pair. There are no lone pairs here. Okay, this shape is called trigonal planar. Planar means flat. Okay, so if I turn it this way, it is absolutely flat. And when you get 3 bonds as far apart from each other as possible, they're going to have a bond angle of 120. Okay, the next one that we looked at, if you look at your drawing, this is another one we've done, look at your Lewis structure for NO2 minus, okay, the nitrite ion. If you look at your drawing, what it looked like, okay, you had nitrogen in the center, a double bond to oxygen on one side, a single bond to the other side, and then you had a lone pair on that central atom. Okay, now I'm not crazy about what angle they're displaying here, but I'll talk about that in just a second. Okay, so this molecule has 1, 2, 3 electron domains. 2 of those 3 have shared pairs, and 1 of the electron domains is a lone pair. Okay, so here's how I want you to think about it. Let me take that away for a second. If we have 3 electron domains, the angle is 120. All right? If I replace one of those with a lone pair, all right, it's not trigonal planar anymore. This shape is bent. Okay? So if you look down here where it says electron geometry, that means like based on the electron domains, 1, 2, 3, that would be trigonal planar, but one of those sides isn't actually another atom, it's a lone pair, so the geometry is bent. Remember what we said, lone pairs take up more space than shared pairs. So ladies and gentlemen, this angle, this is one of the limitations of this PhET simulation. The angle is not actually 120. It's less than 120. It might be like 119. You don't need to know an exact number, okay? All you need to be able to express is that the angle is slightly less than 120. Okay? All right, let's keep moving. Okay. One of the molecules you drew was the phosphate ion, PO4. All right. If you look at your drawing, phosphorus is in the center, and there are 4 single bonds to oxygen. And on paper, it looks like a flat X. But guys, get your brains out of 2 dimensions into 3 dimensions. This has 4 electron domains. All 4 are shared pairs, no lone pairs. This is tetrahedral. The bond angle is 109.5. Right? Let me take one of those out. All right, here's our next example. The one that we drew that looks like this is ammonia, NH3. If you look at your drawing for ammonia, nitrogen is in the center, 3 hydrogens, and 1 lone pair. This has an electron domain, has 4 electron domains. So that's why it says down here, electron geometry tetrahedral. However, that extra lone pair changes that. There isn't a 4th atom here. It's just a lone pair, so the shape is trigonal pyramidal. And again, this is a weakness in this simulation. That lone pair is pushing these bonds a little bit closer together. We would say the bond angle here is less than 109.5. Right? Next one. The example we did for this was H2S. You could also do H2O as this example. 4 electron domains, but only 2 of them have shared pair. The other 2 have lone pairs. This is bent. And again, the angle should be less than 109.5. You don't have to give an exact number. Now, back in Chem 1, for some of you, this is where we stopped. We are going to go on to some more of the exception to the octet rule, exceptions to the octet rule. So let me get rid of these lone pairs. When I asked you to do some drawing of the exceptions to the octet rule, we drew one that was PCl5. Phosphorus was in the center, and 5 chlorine atoms, all with single bonds. This has an has 5 electron domains, no lone pairs. Okay. This has a shape called trigonal bipyramidal. And ladies and gentlemen, this one is a little bit advanced because it has more than 1 bond angle. This bond angle, these are easy. It's just 90. But let me rotate this so you can see. You see that trigonal planar middle here? Okay, that has an angle of 120. So there's 2 different bond angles here. All right, so that's trigonal bipyramidal. The next one, I don't think we drew an example for, but I can give you an example of it. If you were to draw sulfur tetrafluoride, SF4, 4, okay, you would see this. Okay, now, here's the thought process, okay? This is a situation where we have 5 electron domains, again, just like we did in the one we just finished. However, one of the sides is a lone pair. Now, let me take this lone pair off and put this guy back on, okay? Does it matter which one of these atoms I pull off and replace with a lone pair? Yes, it does. And I'm going to give you the world's most ridiculous way to remember how to know which position to replace with a lone pair. Okay? I want you to imagine that this is you. Here's your head. Here are both of your legs. You're standing with your legs together. Here are your feet. Here's your left arm, here's your right arm, and you have a tail. Okay, I know that's ridiculous. Just go with me on it. You have a tail. All right, and you've entered some sort of barbaric situation where some mass murderer is saying, okay, I'm gonna chop something off. What's it gonna be? I know this is getting really dark, okay? If that's me, I'm gonna choose my tail. Okay, that is the thing I can most afford to lose. So I'm going to lose that tail. All right, and look at you now. Here's your head, here are your legs, here's your feet, your left arm, your right arm, and now your tail has been replaced with a lone pair. Okay, the point is, what I'm trying to make in this ridiculous scenario is that you're not going to take off one of these, the top or the bottom atoms. Okay, it's one of the, I think they're called the axial atoms. All right, and this shape is called seesaw. I'm not making that up. Okay, I didn't come up with that name. Let me see if I can get this around so you can see it. Look, it's like a seesaw. Seesaw. Oh, that's all getting floppy. Seesaw. It's not working very well. But it is in the shape of a seesaw, okay? And all you need to say for the angles, slightly less than 90, slightly less than 120, okay? Because it's coming from the electron domain of 5. Okay, next. This one we did do an example of. I'm going to add one more, take one out. No, wait, I messed that up. There we go. Okay. On the examples we drew in our last lesson, if you look at chlorine trifluoride, ClF3, you've got chlorine in the center, 3 fluorines, 2 lone pairs, 5 electron domains. Okay, so it's coming from trigonal bipyramidal, but now you've already lost your tail. Now you're probably going to choose to lose one of your arms. Okay, at least that's what I would do. Okay, I'm certainly not going to lose my head. I'm not going to choose to have both of my legs taken off. I'm going to go with my non-dominant arm. Okay. So that's what I would choose to do. So I've lost my tail and I've lost my left arm now. This is called T-shape. All right, and again, the angle is actually a little less than 90. All right, and I think you guys are starting to get sort of the hang of this. I'm going to go a little bit faster. This is, we did draw this one. This was I3 minus. Okay. 5 electron domains, 2 shared pairs, 3 lone pairs, and look, we're back to linear. Okay, this has a bond angle of exactly 180 because all those lone pairs, yes, they are pushing, but they're pushing equally. So we're back to linear. Okay, now, if you have 6 electron domains, okay, I can give you an example like sulfur hexafluoride, SF6. It would look like this. 6 electron domains. This is called octahedral, and it's 90 degrees all around, no matter how you look at it. Okay. If I go down to the next level, I'm going to take one of those out, replace it with a lone pair. Maybe this is, let me give you an example. Xenon XeOF4. That would be an example of this one. Okay. 6 electron domains, 5 shared pairs, 1 lone pair. Bond angle is going to be slightly less than 90. I know this isn't showing that, but it is. This is called square pyramidal. Okay, if you connected all these lines, it would look like the pyramids in Egypt. The last and final shape that you need to know is this one. Okay, and if you did xenon tetrafluoride, XeF4, you would see 6 electron domains, 4 shared pairs, 2 lone pairs. And ladies and gentlemen, this is called square planar. Remember, planar, flat, and it's 90 all around. Okay, so those are all the shapes that you need to know. Okay, we talked about the bond angles. We talked about how the lone pairs cause the angle to be a little bit smaller because lone pairs take up more three-dimensional space than shared pairs do. Okay, the next thing we're going to talk about is how to determine whether these molecules are polar or not. And just to be clear, you know, those of you that are my students that are watching this, you have access to this chart. Okay, and if you look what we've now gone through, okay, this is electron domains, this is the number of shared pairs, this is the number of lone pairs, okay? This is the shape, and the bond angle is also here, okay? The polarity of these molecules is also there, okay? But we're going to talk about, without having the chart, how do you know? So there's some things to consider here. Okay, first of all, your molecule has to have at least one polar bond in it. And without an electronegativity chart in front of you, you should really just interpret, if you see a bond between 2 different elements, it's a polar bond. Okay, between 2 different non-metals, it's a polar bond. But the big thing to consider is the geometry. Okay, so if you are looking at a shape that is symmetrical, and you can't say the word symmetrical on the AP exam, you would say a shape that cancels out the polarity of those bonds. Okay, here are some examples. Like we drew carbon dioxide, which was linear. Okay, there's a double bond here and a double bond here. Each one of those bonds is polar. Those C to O double bonds, each one is polar. However, the linear shape cancels out the polarity of those bonds. For those of you that are familiar with vectors, okay, it's like the polarity vectors are pointing in opposite directions and they cancel each other out. So CO2 is a non-polar molecule. Trigonal planar is another shape that can cancel the polarity of the bonds. Now, of course, guys, this is assuming, and it even says this on your chart, this is assuming that the terminal atoms are all the same element. Okay? If any one of your terminal elements is something different, then it's automatically a polar molecule. Okay? But assuming that the terminal elements are the same, trigonal planar is a shape that would cancel out the polarity and would result in a non-polar molecule. Okay. Here's some examples, and this is not all of them, but just examples of shapes that do not cancel out the polarity of bonds. Bent, for example. Like this could be a drawing of water in front of us. Water has a bent shape. Okay, here's oxygen, hydrogen, hydrogen. That's a polar bond, and that's a polar bond. And look at the vectors. Okay, they are not canceling each other out. The right-hand side of water carries these arrows are actually pointing the wrong direction. If this were water, the oxygen side of water, because it's polar, carries a slight negative charge. The left-hand side of water carries a slight positive charge. There's a little bit more electron charge piled up on the right-hand side, the oxygen side, than the hydrogen side. So bent is a shape that does not cancel out those polarities. Trigonal pyramidal is another example, like ammonia. Okay, nitrogen is on the top, hydrogens are on the bottom. The nitrogen side, because it's the more electronegative element, this side is the nitrogen side is going to have a little bit more of a negative charge. The bottom side will be slightly positive. So what I would like for you to do, you have 10 molecules in front of you, and this will take you a little bit of time, but it's good for you to practice. I want you to draw these out, predict their molecular shape, the bond angle around the central atom, and tell me if the molecule or ion is polar or nonpolar. So pause your video and we'll check your answers. All right, let's see how you did. I wasn't able to fit it all onto one page, so it's on multiple pages. So I've given you the Lewis structure, the molecular shape, the geometry, the angle around the central atom, and the polarity of the molecule as a whole. Okay, so there's the first 4. And if I'm going too fast, you can always pause the video. Okay, there's the next 4. I tried to write as neatly as possible. And then I believe there's one more page, the last 2. Okay. So at this point, we've learned how to draw them, learned how to predict shape, angle, polarity. There's one last piece. It's called hybridization. So let's get to it. That's the last piece to this puzzle. Okay. If you guys think about what the term hybrid means, like a hybrid car, or you think back to biology, those dihybrid crosses, and maybe that brings up happy memories, or maybe that triggers PTSD for some of you. Hybrid always means a blending of 2 different concepts. Like a hybrid car is blending gas power versus electrical power. Okay. So what are we blending? What are we talking about here? What are we blending in chemistry? We are blending orbitals. Okay, now that's a word we really haven't used much since our last unit when we were talking about electron configurations. But the reason that this happens, and there's not like some magic person making this happen, this is what occurs in nature. The orbitals blend because that leads to a minimum energy for the molecule. Okay, so I'm going to use methane here, CH4, as an example. And if you guys will recall, we've drawn methane a few times now. Carbon with 4 hydrogens joined to it has a very simple shape that looks like that. Okay? 4 electron domains, 4 shared pairs, that's tetrahedral. Okay? Carbon can form 4 bonds. It obeys the octet rule. This we know. Okay, fine. Well, here's the thing though. If you were to look at where carbon is on your periodic table, carbon has 4 valence electrons. And if we thought back to our previous unit and drew out those 4 electrons in what we called orbital notation, this is what it would look like. Okay, now, let's remember what a covalent bond is. All right, it's a pair, one pair of shared electrons, one electron coming from one atom, the other electron coming from the other atom. Each atom contributes 1 electron and they share. If you look at the way I have drawn carbon's 4 valence electrons, this looks to me like carbon can only form 2 bonds because these guys are already paired up. So the way that it's drawn here, this looks like carbon can only bond with 2 things when we know that carbon always forms 4 covalent bonds. Here's what happens. This is sort of a phenomenon of nature. One of those valence electrons jumps over there. It doesn't stay in 2s. It jumps over to 2p. Now look at the arrows. Now doesn't it look like carbon could bond 4 things? And it can. And ladies and gentlemen, that is what happens. So that's the first part of this picture, is that electrons don't have to stay in the orbitals that we predict that they'll be in. Okay, so that's the first part of this picture. Okay. Now, we talked about shape of the sublevels in our last unit. S sublevels have a sphere shape, and P sublevels, P orbitals, have what's called this is called a dumbbell shape. Okay, so there's 1 s orbital, and there were 3 p orbitals. Okay, if you'll recall, let me just draw it again. For carbon, we had 1 electron in the s, and because that 1 moved over, we had 3 in the p. Well, guys, let me ask you a question here. Do these 4 shapes in front of you, do they look identical? No, they don't. 3 of the 4 are the same shape, but the 4th one isn't. And that's a problem, because I know that in this molecule of methane, these carbon to hydrogen bonds have shape to them, ladies and gentlemen. I'm not sure if you knew that, but they do. Bonds have shape to them. Those 4 bonds in methane are identical in shape, but wait a second. This picture with the blue ball and the pink things, that doesn't look identical to me. And that is the essence of hybridization. Watch what happens. Those 4 different shapes blend together to form 4 identical shapes. Would you all agree that these 4 in the middle, they are identical in shape, and they come together to form this tetrahedral shape? So what got blended together? 1 s orbital and 3 p orbitals were blended together. So ladies and gentlemen, that carbon in methane, we say is sp3 hybridized. Okay, it has sp3 hybridization because what did we blend? 1 s orbital and 3 p's. Now, energy-wise, why does this really happen? Because the hybridized situation is at a better energy state than leaving them separate. Okay, so this is what happens in nature. Okay, so when you're given a molecule, okay, you can predict the geometry, you can predict the shape. And here's the thing. There's a lot written on this slide, but here's the take-home message. Ready? Hybridization depends upon the steric number. Remember, another term for that is electron domains. It depends upon that only. So wait a minute, what am I trying to say here? All right, if you all will, those of you that have this chart, I want you to notice, wait, I'm backwards here, right here, okay? All of the shapes that have 4 electron domains, look over here in the hybridization column. sp3, sp3, sp3. Okay, there's 4 electron domains, ready? So what's the hybridization? Okay, there's 4 domains, ready? S, P1, P2, P3. Anything that has an electron domain has 4 electron domains will have a hybridization of sp3. That includes bent and trigonal pyramidal. I mean, let me just draw something for you real quick. You know, if I have water, water has 4 electron domains around it. It doesn't matter that some are lone pairs and some are shared pairs. Doesn't matter. It has 4 electron domains. This is sp3. Ammonia also has 4 electron domains. Guess what? It's also sp3 hybridized. Hybridization depends upon the steric number or number of electron domains only. Okay. sp2 hybridization. Okay. Focus your attention, ladies and gentlemen, on one carbon only. Just this one carbon. Okay. Remember that electron in carbon is going to jump, and it does that again. S and P. Okay. Focus your attention around that carbon that I just circled. How many electron domains does it have? It has 3. Remember, a multiple bond counts like one side. So 1, 2, and this counts as a third. So how many orbitals do I need to hybridize? Not 4, just 3 this time. Okay, and I do realize, I know that that's going to leave an extra electron there. We'll talk about what happens to that extra electron in just a minute. Okay, but remember, hybridization is based on the number of electron domains only. This has 3 electron domains. Okay, so 3 electron domains. What's the hybridization? Ready? S, P1, P2, sp2. Anything with 3 electron domains is sp2 hybridized. Okay. So we're going to blend 1s, 2 p's into 3 identical shapes, and look, there's that trigonal planar shape that is around this carbon right here. Okay. Again, I realize that there is that extra electron that we had, and I'll talk about that in just a second. Okay, this is what that whole molecule looks like. Please don't panic. You're never going to be asked to draw something like this. Okay, but that is what C2H4 looks like in 3 dimensions. Can you see that trigonal planar around the carbon there? Okay. Now, that extra electron, that I did not hybridize, that I did not use, that's an unhybridized orbital. And guess what? That one electron, you know what it's doing? It's doing a figure 8 above and below the plane here. So that's what that extra electron is doing. And guess what? The other carbon in the picture, let me go back. This carbon has an extra electron as well. So he's bouncing around over here, okay? And this pair of extra bouncing electrons forms something called a pi bond, okay? Please don't worry about these weird drawings. This looks like an eraser to me, okay? The point is, a sigma bond are formed from those hybridized orbitals. A pi bond is formed from a pair of unhybridized orbitals. Okay, now I don't want you to get really hung up on like being able to draw a sigma or a pi bond or explain what a sigma and a pi bond is. All you're going to need to be able to do is to count sigma and pi bonds. Okay, and let me go back up to that drawing again. Okay, ready? Here we go. How many sigma bonds are in this drawing? This is the extent of what you would be asked for sigma and pi. Are you ready? Here we go. Here's how many sigma bonds there are. 1, 2, 3, 4, 5. There are 5 sigma bonds. How many pi bonds are in there? Let me change color here. There is just 1 pi bond. Okay, so pi bonds only show up in a multiple bond. Okay, a double bond is 1 sigma and 1 pi. A triple bond would be 1 sigma and 2 pi. All right, so please do not get hung up on, defining sigma and pi, but technically speaking, a sigma bond is formed from the hybridized orbitals. Pi bonds are formed from unhybridized orbitals. Okay, but you just need to know how to count them, that's all. All right, so here's, again, do not worry about trying to draw this. Okay, this is showing the sigma bonds, okay, and this huge pink thing is showing a pi bond. But if that drawing is confusing to you, don't worry about it. Okay, let's wrap this up. Okay, look at this central carbon here, guys. How many electron domains does this carbon have? 2. 2 electron domains. Okay, so 2 electron domains. Guess what the hybridization is? sp1. That's it. Okay, or we would just say sp. All right, so this is sp hybridized, that carbon. Okay, that leaves 2 extra electrons that are not being used. Okay, and let me go back. Let's count sigma and pi bonds. Since there's 1 sigma, there's 2 sigma, 1 pi, 2 pi. There's 2 pi bonds. Why are there 2 pi? Because there's 2 unhybridized orbitals. All right. That's what carbon dioxide looks like in 3 dimensions. This is really getting kind of complex here because we have a pi bond there and a pi bond there, and they're not in the same plane. Okay, that's getting a little more complicated than we need to be. Okay, now before we do some practice, here's some good news. All right, on the front side of this chart, where you have electron domains 2, 3, and 4, you need to know the hybridization, and that's easy. It's sp, sp2, sp3. Here's the good news. Are you ready? On the other side, with these extended shapes, you have my permission to completely scribble through the hybridization column there. Because on these extended shapes, the jury is still sort of out as to whether hybridization even exists in those molecules. So until the scientific community makes up their mind, the AP exam is not going to ask you about hybridization for electron domains 5 and 6. Good news, right? So let's look at a practice question. It says, using the diagram below, first, determine the hybridization around each one of those atoms that I've labeled A, B, C, D, and E. Then I want you to answer the question, a student claims that all the atoms in the molecule exist in a single plane, like the whole molecule is totally flat. Do you agree with the student's claim? Explain why or why not. So I want you to pause the video and see if you can answer these questions. All right. So let's go atom by atom. What is the hybridization around each one? Remember, hybridization is just based on the number of electron domains. So atom A, this carbon, has 3 electron domains, so that's sp2. This one has, I'm sorry, I put the letter over, there is a bond there between N and H. This has 4 electron domains, so this is sp3. This carbon is sp2, this nitrogen is sp2, and this carbon is also sp2. All right. A student claims that all the atoms are in a single plane, totally flat. Okay, well, let's think about the geometry around each atom. So atom A here, this carbon, that's trigonal planar. Okay, that's planar, flat. This has, think about what geometry? 4 electron domains, 3 shared pairs, 1 lone pair. That is trigonal pyramidal. Ladies and gentlemen, that is not flat. This one is flat, that's trigonal planar. This one is bent, that's flat. This carbon is also flat, trigonal planar. But because of this one nitrogen here, all right, it is not flat. So basically this whole molecule is flat except for this one little hydrogen sticking up out of the plane. Right, so that's how you would explain it. The last thing that I want to say here, now that we know about sigma and pi bonds, okay, remember a pi bond was that extra bond in the multiple bonds, okay? Sigma, this is the sigma symbol, can be described as localized, okay? We've seen that word before. Sigma bonds don't move around. Okay, the electrons that are involved in those bonds stay put between the 2 atoms that they're involved with. However, if you're looking at a situation where resonance exists, that bond that is jumping back and forth, moving locations, okay, remember we drew a molecule that had double bond on the left and it had a double bond on the right, and I said it's not really in those positions, it's actually kind of an average of those 2. The electrons that are split between 2 locations, it's a pi bond. Those electrons in a pi bond are described as delocalized. They can move around. Okay, so those are just 2 examples of molecules that exhibit resonance. Okay, you can draw more than one structure for them. And if you're ever asked to explain resonance, okay, you are permitted to use the term pi bond if you want. You can simply say there is a pair of electrons resonating between two locations, or you can say there is a pi bond resonating. You can describe them as delocalized electrons. You have options here. And I just wanted to go over that with you and just show you that you have some more vocabulary available to you. So, whew, that was a lot. Thank you for sticking with me. Even if you had to take a few breaks, that's cool. I might have taken a few myself. But I appreciate you sticking with me, and we have just now finished Unit 2. So I hope that you learned a little something today, maybe a lot of something today, and I look forward to seeing you for Unit 3.